Alright, students, so let's discuss a problem based on heat exchangers. Alright, so the problem is a counter flow, right? So these terms are very important, right? A counter flow, double pipe, heat exchanger, right? The short form, let's call it HE, right? Heat exchanger, right? Is to heat water from 20 degrees Celsius to 80 degrees Celsius, right? At a rate of 1.2 kilograms per second, right? And the other most important thing is that the heating is to be accomplished by geothermal water available at 160 degrees Celsius at a mass flow rate of 2 kilograms per second, right? Fine. Also, it was given that the inner tube is thin walled and has a diameter of 1.5 centimeters. If the overall heat transfer coefficient of the heat exchanger is 640 watts per meter squared per degree Celsius, calculate the length of the heat exchanger, right? So that is the problem. So now here first let's make a little sketch, right? So now you need to understand, right? Now there are two types of fluids, right? And why we use a heat exchanger, right? That is in order to execute the transfer of heat between two fluids, right? We have one fluid is a hot fluid, right? And while the other fluid is the cold fluid, right? So now just make a very simple sketch, alright? Alright. So let's call this part as the shell, right? Shell, or we can also call it the larger tube, right? And inside that we have the smaller tube, right? Or if we call this part as the shell, right? Let's call this part as the tube. Alright. Now also it was mentioned that here the type of the flow that we have is a counter flow, right? That means if I are going to consider the counter flow, right, the direction of these two types of flows are opposite to each other, right? So then, right, so let's sketch this like that. Now from this left end, right, we have the entry of the cold fluid, right? So let's call it like that. Right. From this side we have the entry of the cold fluid, right? Let's say cold fluid in, right? And our short form for the temperature is TCI, right? TCI, cold fluid inlet temperature, right? This side we have cold fluid outlet, and so let's call it T cool out. Alright? Yeah. And from this side, what do we have? From this side we have the hot fluid inlet, right? So now you can observe the direction of the two fluids are actually opposite to each other, alright? So so like that, the hot fluid exits from here, right? Hot fluid exits from here, so let's call it T hot out. T hot out, and from this side T hot in. Alright? Yeah. So now, what is the theory? We can say heat released by hot fluid equals what? Heat gained by cold fluid, right? And also now we have already sketched a simple layout, and now let's sketch the temperature and distance profile, right? So this is the temperature, right? And this is the length. We can actually call it the length of the heat exchanger, right? Length of the heat exchanger, or the length of the heat exchanger from the respective or from the respected inlets, right? I mean, like, simply we want to sketch how the temperature varies with respect to the length of the heat exchanger, right? And also you can observe the inlet of the cold fluid, and if I go to consider the inlet of the hot fluid, these two inlets are at completely at opposite ends, right? So not at the same end, right? Because if I go to consider this left end, inlet of the cold fluid is here, and we have the outlet of the hot fluid, right? That means inlets of both the fluids are not designed at the same end, right? So that is the idea. So now just dotted line, right? So this is how the temperature varies for the hot fluid, right? All right. So this is a decreasing curve. T hot in, T hot out, right? And this is for the cold fluid. Here we have cold fluid inlet, cold fluid outlet, T cold out. All right. So now, what is the equation that we are going to use here for this heat exchanger? All right. The heat transfer rate, right? So measured in watts, right? Heat transfer rate, let's call it Q dot, that equals overall heat transfer coefficient Q, area of the heat exchanger, right? The net area of the heat exchanger, right? Times, I will put square brackets, right? LMTD, mean logarithmic mean temperature difference, right? All right. So now also we have, now this is the equation that we are going to use, right? So now, all right. So first of all, we will see how can we find LMTD, right? We'll check that first. Logarithmic mean temperature difference equals, remember these notations, right? Delta T1 minus delta T2 divided by ln delta T1 divided by delta T2. So this is the equation. So now the target is, how can we find that? How can we find delta T1? Delta T1 equals T hot fluid inlet temperature minus T cold fluid outlet temperature. Now this formula is valid only for the counterflow type, right? So that is how you should find delta T1, and delta T2, T hot fluid outlet temperature minus T cold fluid inlet temperature. So now, what are the things that we actually know? What is the hot fluid inlet temperature? Geothermal water. Now geothermal water is the hot fluid available at 160 degrees Celsius. So hot fluid inlet temperature is 160 degrees. No worries. What is the cold fluid? The cold fluid outlet temperature we know that is 80 degrees. No worries. So 160 minus 80, 80 degrees of Celsius. Alright. 160 hot fluid inlet minus 80 cold fluid outlet. 160 minus 80, we take 80, right? And what is the hot fluid outlet temperature? So that is not given, unknown. I'll put a box there. Hot fluid outlet temperature we do not know. Okay, doesn't matter, let's keep it like that. Minus what is the cold fluid inlet temperature? That is 20. So now, this is how we have to find that. Alright. So I will use the space above here, right? Just erase that. So now we know the total heat that is released by the hot fluid, right? That equals to the, the total heat that is released by the hot fluid, that equals to the heat gained by the cold fluid, right? So Q dot, let's say heat gain for cold fluid, that equals what? M dot, like in terms of mass flow rate, times specific heat capacity times the temperature difference, right? What is the temperature difference? T cool out minus T cool in. What is the mass flow rate of the cold fluid? Heat exchanger to heat water from 20 to 80 at a rate of 1.2. So mass flow rate is 1.2. Specific heat capacity 4.184 kilojoules per kilograms per Kelvin, right? Times the temperature difference, how much? 80 minus 20, isn't it? Yeah. So what will be the answer for that? So let's calculate. 1.2, 4.184, temperature difference 60. 301.25. 301.25. How about the units? We have the units will be Kelvin to Kelvin will get cancelled, kilogram to kilogram, so kilowatts, isn't it? 301.25 kilowatts. Alright. So this heat gained by the cold fluid, this 301.25, that value will be equal to the heat released by the hot fluid and also the total heat transfer rate if you are going to consider the entire heat exchanger, right? So if you are going to consider this equation, that Q dot equals overall heat transfer coefficient area of the heat exchanger times LMTD, right? Alright. So now this value is known now. What is this value? This is 301.25 kilowatts. I hope that part is clear, right? So this value, let's equate that to the hot fluid. Alright. So what we can do? Now I am going to apply the same equation, this m dot Cp, that temperature differs to the hot fluid. Alright. So then let's call it 301.25. Now what is the mass flow rate of the hot fluid? That is 2 kilograms per second. Now specific heat capacity of geothermal water. Now if you are going to consider specific heat capacity of geothermal water, if you are going to consider geothermal water, that depends upon the temperature of geothermal water and pressure and also the mineral content, right? But let's consider, as for this problem, let's consider that value is given, right? So let's consider that value is given to you, the specific heat capacity for geothermal water that is given to you as, let's consider that is 4.31 kilojoules per kilograms per Kelvin. Remember the units, right? Temperature difference we don't know, so that will be 160 minus one unknown value, that is T hot out, THO. So let's do the simplifications. We have 1.25. I will put other values to the denominator, right, to the left side, right? All right. All right. So I'm getting the value as T hot fluid outlet temperature as 125.05 degrees Celsius. 125.05. So now we know that it is 125.05. So it is 125.05. Right? All right. So now we can find what is delta T2, right? What is that? 120, 105. So 105.05 degrees Celsius. Alright. So now we can calculate this one. What is delta T1? 80 minus 105.05 and ln 80 divided by 105.05. What is the answer? What is the value for LMTD? 80 minus 105.05 divided by ln 80 by 105.05, 91 point, LMTD I am getting as 91.957, let's round that, 91.96 degrees Celsius. 91.96, right? So now that is known. Alright. I hope everything is clear, right? So now in order to take some space, right, I will erase this part, right, because I need some space, right? Alright, so let's erase up to here. Alright, right. So now what is the problem? We need to find what is, we have to find the length of the heat exchanger, right? So before that, so now let's consider this equation. Alright, so what is the equation that we can use for the entire heat exchanger? So that we can use Q dot equals overall heat transfer coefficient times area of the heat exchanger times LMTD. So what is the heat transfer rate? That is okay, that we already calculated. That is 301.25. 301.25. But remember in kilowatts, overall heat transfer coefficient of the heat exchanger is what? 640. But be very careful. That is watts per meter squared per degree Celsius, right? That is in watts. So better you can keep that with respect to the same units to equalize the units, right? So this is given in watts per meter squared per degree Celsius. So let's convert that 640 to kilowatts per meter squared per degree Celsius. So 640 divided by 1000. or you can convert this value into watts, right? Doesn't matter, right? So that is why I divided this by 1000, right? So 301.25 equals 640 to 1000, equal as the units. Area, let's keep it like that. Area will definitely come in meter square, right? LMTD, what is the value of LMTD? 91.96. So if you carefully do the simplifications, what is the value for area that you are getting? 301.25 and area 5.118 meters squared. 5.118. So let's call it 5.12 meters squared. Right. So that is the area of the heat exchanger, right? So, and for this area of the heat exchanger, there is another equation that is called pi times diameter of the smaller tube, right? Or the diameter of the tube, pi d, pi diameter of the tube times the length, pi dl. So this is the other equation that we need. If you don't know this equation, then you might not be able to finish the problem, right? Area equals pi times d times l, right? So what is the area? So what is this area? So let's write it here. Okay, so let's erase this part. Okay, I hope you have already taken that clearly, right? So all right, so what is the area? That is 5.12. I'll write it with the top, 5.12 in meter squared, right? And pi, now diameter of the tube is given in centimeters, right? So 1.5, we have to keep that in meters. So 1.5, so divide that by 100 times L. So what is the value of L? 5.12 divided by 5.12 divided by 5 divided by all right, I'm getting the length as 108.649 meters. So you can call it 109 meters, right? Or if you want, you can even keep like that, it's okay, right? So that's all about that problem, right? We will discuss some more problems in upcoming videos. Thank you very much.